Okay. Uh, Good morning, and we will start today's class. I'm recording the lecture. What I want to discuss is a few intricacies about diene ligands. Acetylene and dienes together in two short videos, which I posted on the web. I hope you had an opportunity to go through it. What I'm going to do is to quickly review some of the structures, compounds, and those of you who might have had some difficulty in viewing them, I thought I will just also going to have some components of the discussions that we had on Friday. The first thing that I want to tell you is that diene ligands are a very simple extension of the alkene system fairly thoroughly. Their dienes are, we are talking about conjugated dienes, not isolated double bonds. Isolated double bonds are also common. Something like this, for example, they can be considered as two alkenes, which are what we are going to specifically talk about dienes. There are several complications in these systems, primarily because of the way in which it can be oriented and also extent to which you can distort the metal from the plane as a plane. The simplest system that I discussed, simple system that I discussed in the first class or in the first lecture was the one where all these atoms belonging to the organic component, organic diene component, lying on the same plane. So the 4 carbons plus the 6 hydrogens are in one plane, and the metal is above or below this plane. But this rarely happens because of various reasons. One of them I mentioned, and that is the interaction between the 2 hydrogens, which are sterically sometimes constrained, it and moves the hydrogens out of the plane. In the case of trans geometry, you do not have this problem. The trans geometry does not have this problem. But then the overlap steric congestion are concerned. Now I will talk about some of the electronic factors. One factor that we talked about was the interaction of an ene with the metal. Let me go back to the ene, simple ene. Is that the extent of back donation from the metal into the pi star orbital of the olefin and the extent of forward donation from the olefin to the metal, if they are very significant, then what is going to happen is that the pi bond completely disappears. If the pi bond disappears, that means it's a single bond, and you can think of 2 single bonds between the metal and the carbons, right? In such a scenario, you have a metallocyclopropane. So this metallocyclopropane description is an alternative description to the simple Duerchat-Duncanson model. In fact, some complexes are having such long carbon-carbon bonds. This carbon-carbon bond is so long that it might be appropriate to call them metallocyclopropanes and not pi complexes. Let me now extend that to alkynes. If an alkyne is so elongated that it now becomes a metallocyclopropene. So, yes. Arnab, can you switch off your microphone, please? Thank you. Okay, so the alternative description is a metallocyclopropene. And this is particularly important in the case of systems where you have strained alkyne. Okay. So let me quickly show you. So the first structure that I want to show you is the first structure is a metallocyclopropane type of structure, is the one that is formed between TCNE, that is tetracyanoethylene. If you can see, as I hope you can see the crosshairs, this is a cyano group. So 4 cyano groups are attached to 2 carbons. So this is actually tetracyanoethylene bonded to nickel. Nickel is in the zero oxidation state. Nickel is in the zero oxidation state, and so this is a system which has a lot of pi back donation. Unfortunately, I cannot. And as a result, the bond distance is in fact 1.476 in this case. Close. This is one carbon, this is the other carbon, and metallocyclopropane. To be expected. They are all sigma bonds. So this is one system where you have significant elongation and formation of the metallocyclopropane to choose between several windows which are open, so please bear with me. This is sorry, that was not the right one. This is okay. This is dicyanoethylene. That is also an example, but that's not really what I wanted to show you. I wanted to show you a benzene complex, and it is, yeah, this is a complex that I wanted to show you. Here is a benzene molecule, and the benzene molecule is now coordinated to a nickel again, and the nickel has got two diphenyl phosphinoethane molecules which are coordinated to it. But notice the geometry of the benzene. The benzene is flat, and carbon-carbon unit is also in the same plane. Okay, so this is perpendicular to the pi plane, which is there on the benzene. This is a benzene, or if you think of this as a benzene molecule, the benzene molecule is having a pi set of pi orbitals which are perpendicular to the plane in which the nickel carbon nickel unit is present. Okay? And that's the same. What is surprising is that the same plane is also containing the two phosphorus ligands. Okay, let me label the phosphorus units also. So the orange color atom is the phosphorus atom. So you have two phosphorus atoms and two carbon atoms, as if it is a square planar complex. So that is very significant, and it's almost like nickel 2 plus. So it is like a nickel 2 plus coordinated to two carbons. So two anionic ligands present on the nickel 2 4 coordinate complex. Okay, one more to acetylenes. Acetylenes, I wanted to show you two examples. Let me see if I can get that. Yes, the simple example is this one. This is present, and the cyclopentadienyl units are coordinated to molybdenum. So this is the molybdenum 2 complex coordinated to acetylene. Once again, you notice that the phenyl groups are bent away from the molybdenum. Acetylene has got cylindrical symmetry. I will explain the 4 pi systems, 4 electron donation capability of acetylene shortly. But then the two electrons that are donated to the molybdenum in this particular case makes the system almost like an sp2 unit. And so if I want to show you the angle, this angle is now away from, this is 30, 90 plus, okay. That is 50 degrees away from what you would expect if acetylene was linear. If you think of this angle, this is 146. So it has deviated away from 180. So that's only 30 degrees. Sorry, this is 30 degrees away from linearity. And if you look at it as 120 degrees, this is only 20 degrees away from the 120 degree angle that you would expect for an sp2 system. So this is no longer like a simple complex. This is a complex where there is a significant bending. Now look at this unit. This is the two pi bonds of acetylene are perpendicular to each other. And so I told you that the two cobalt atoms of CO2, one of the carbon monoxides has been replaced by phosphine in this instance, but that is immaterial. But imagine there is a CO here. CO2, CO6 is an excellent protection agent for acetylenes. So this is diphenyl acetylene. The diphenyl acetylene is now coordinated to two cobalt atoms. And let's take a look at the distances. This distance is now 1.4 angstroms. That is almost like a double bond. So the coordination of the two acetylenes has significantly increased the bond distance between the two carbons. Okay, and notice that the set of four atoms, which I can let me just label the four atoms so that you can see it clearly. These are the four atoms that we are talking about. Two carbon atoms belonging to the acetylene and two cobalt atoms which are bonded to each other. So this is almost like a tetrahedron. I hope you are able to see the tetrahedron. So the two pi bonds of acetylene are almost perpendicular to each other. And so if I were to measure this angle would be this angle should have been 90 degrees. It is 780 degrees right now. So it's 10 degrees away from the perpendicular angle that you expect for two pi systems independently interacting with the atom. Let me just go through the last example, which was a complicated example I showed you. Here, these things move about, it looks like, on the screen here. So here you go. This is three acetylene molecules bonded to tungsten. This is a tungsten now. This is a tungsten. The acetylenes are, the two carbon atoms have been selected. They have a sulfur. Notice how the three acetylenes are bonded as if they are spokes of a wheel around the tungsten, and it has got threefold symmetry. If you look at it through the carbon monoxide tungsten bond, you find that it has got threefold symmetry. That I showed you, that is neither 4-electron donor or a 2-electron donor. The total number of electrons it satisfies the 18-electron rule. It's not a 20-electron complex. Now, let me just explain how the acetylene can donate two pairs of electrons, and this is something which I showed you in the last video, but let me now show it to you in okay, this is acetylene molecule. I hope to see the acetylene molecule, and the atoms are labeled. 1 and 2 are carbons. This is a bit difficult because the mouse, yeah. So I hope you're able to see the 4 atoms now. Now let me show you the other pi bond. So these are the 2 pi bonds, right? Now I have a system where I have added these 2. Suppose I add these 2 pi. These 2 are at the same energy, minus 4.05 atomic units. Okay, so minus 0.405 atomic units, and notice that 2 pi bonds are perpendicular to each other. They are degenerate or equal in energy. Now it approaches in this direction. In this direction, it can interact only with this pi bond. This pi bond. Okay, that's what the cobalt atoms did. Now, if a molecule, or if a fragment comes perpendicular to this, in between these two, in this angle, if it comes in this angle, I can form a linear combination of these two molecular orbitals. These two then can form a bond with a metal which is approaching in between the two pi systems. Now notice that this cylindrical symmetry holds good only if there is no other atom or interacting species in the vicinity of the acetylene. The moment you approach it with the metal, the cylindrical symmetry completely disappears. So that is the reason why you tend to have some confusion in your mind. The moment you approach it with the metal, linear combinations can be formed. And that is what is envisaged when you say that the acetylene is giving 4 electrons. This pi system and the perpendicular pi system, both of them are combining together, forming two separate molecular orbitals which have a different symmetry, which I showed you in the previous video, and that is resulting in donation of 4 pi electrons. Now let me go to another intricacy of a diene, and that is, let me see if I can go back to my okay, let me remove all these things from the screen. I have to remove one by one, yes. Sorry about that. Maybe I can switch completely like this. Hold on. Yes. Okay. So now I want to talk to you about the bond order changes. The bond order changes in simple dienes. Let me review. I don't have it. Let me draw it for you. So here is the I will draw only one side of the pi system. So this is the psi1 or the lowest energy molecular orbital. Then the psi2, had this symmetry where there was only one node, and the psi3 had this symmetry. Okay, and psi4 obviously will have alternate shaded units. Okay, so when the metal approaches the butadiene, it sees a symmetric system, and the bond order in this symmetric system is, in fact, this has got 2 electrons, this has got 2 electrons, right? So the butadiene, for example, has got 2 electrons in both of these pi molecular orbitals, and so the bond order between these two carbons, C1 and C2, was in fact close to 2. I'm saying close to 2 because the 2 electrons are, in fact, in the case of psi1, there is a pi bond which is making a bond between C2 and C3. So as a result, what will happen is the pi bond order between C1 and C2 is only going to be slightly less than 2. You have a total of 4 electrons in these two molecular orbitals, and the pi bond order is going to be slightly less than 2 in the case of the diene. Whereas in the case of the simple ene, you ended up with a pi bond order of 1. Okay. here it will be less than, the pi bond order is going to be less than 1 because it is now shared between C2 and C3. There is some delocalization which reduces the pi bond order. But if you go to side 3, the pi bond order between C2 and C3 increases. So if you populate it by moving electrons between side 2 and side 3, you will end up increasing the pi bond order between C2 and C3. It will start looking like this. If you populate side 3, you end up making the molecule look like this. That means C2, C3 distance will come down and C1, C2 distance will increase. Okay. So now think of the system where you have populated side 3 as a result of back donation and you have depopulated side 2. What you are doing is you're decreasing the bond order between C1 and C2 and making C2, C3 look shorter, or rather C2, C3 look like a double bond. So that's what is going to happen when you have these two extreme descriptions are going to make the diene molecule look like this. You can think of it as two pi complexes where the metal is bonded to the two double bonds in an isolated fashion. That's what I've shown you on the top. On the top, this is looking like this. Two pi bonds interacting with the metal. And in the extreme description, when you have sufficient pi bonding, you end up with this description, okay, where you have the C2, C3 forming a double bond and C1 and C4 forming a sigma bond to the metal. So that is the reason why some of the complexes, especially when you have titanium and zirconium and so on, these complexes, or actually I think I have a zirconium example, so let's make it zirconium. So you end up with a metallocyclopentene description. This is a metallocyclopentene. So this is the reason why the bond distances, one of you has asked why this bond distance is longer in the picture. So that's the reason why you have this longer distance between C2 and C3 and shorter distance between C1 and C4 and the zirconium. Okay, so this looks like a metallocyclopentene. You might think, why is this true happening for zirconium and not for the iron complex that I had shown you, where you have a uniform bond distance between C1, C2, C3, C4 and the iron atom. And that can be explained because you do the electron counting, you find that this is now having a weak interaction between the zirconium and the pseudo double bond that is formed. So you can end up with electron count you include this weak interaction plus weak interaction. So you can understand why the zirconium likes to form a metallocyclopentene description. Okay. So many of the niobium and zirconium complexes have got this type of description, this type of a bonding. And This is also true for this is DBA is dibenzylidine acetone. But this dibenzylidine acetone, in fact, is not a good diene because it has got I mean, it's got a conjugated system, but it's not conjugated in the traditional sense. So this is a complex where two palladium atoms are bonded to the two double bonds. Three of the ligands, dibenzylidine acetones, are there for two palladiums, and they are present just like in the tungsten complex in a threefold symmetry. Okay, I have a structure for it, but I think I will skip showing you that to save time. Okay. I have said here, why is it that the S-cis is a better arrangement than the S-trans? I really do not have a good answer for it, except to say that the S-cis has got this problem with these two hydrogens. And that's the only reason the S-cis can be a better arrangement. Apart from that, I do not have a good answer to give you why the S-cis should be really a better arrangement, because it seems to me that the overlap will be poor. You can draw the molecular orbitals, and the electronic reasons are not very strong, but definitely the electronic reasons seem to suggest, if at all there is something, it has to decrease in overlap. So I think the only reason can be steric reason. But if you can think of some better reason, let me know. Okay. So let me now go to another diene, which is a very strange system, and that is that of cyclobutadiene. Cyclobutadiene is these are actual MOs calculated, and the pi MOs, which are shown for you here, and you notice that they are isolated double bonds, which means this is a rectangular cyclobutadiene. Although it may not be obvious to you because these are opaque orbitals, this is a system which has got, for exaggeration, I'm doing it like this. That's not a very good drawing here. So this is the geometry that has led to this type of an energy distribution. So you can see that the C1, C2, C3, C4, C1 and C2 are more strongly bonded than C3 and C4. And you can see the position of the double bonds in this picture, because you can see the double bonded notation right here. Okay, so this is the way in which it is present. If I draw it in a square fashion, I would end up with a molecular orbital energy level diagram, which will be like this. And so if I have 4 electrons, I will end up with the triplet state as a ground state. So here, of course, this would be filled like this, but this is for a square cyclobutadiene. Okay, so this, what you are seeing on the screen, is actually a rectangular cyclobutadiene. That's a singlet. But what transpires is that this rectangular cyclobutadiene, which is the ground state of cyclobutadiene, when it was coordinated to FeCO3, it became a square. And this was predicted even before the synthesis of this molecule. This molecule itself was predicted before the synthesis, and this was done by 2 theoreticians, These are two theoreticians. Orgel is the same person as the Orgel diagram, whom you might have encountered in your coordination chemistry classes. So this is Orgel and Longworth-Higgins in 1956. This is the year. These are the pages, by the way. So it was predicted in 1956, and then later it was synthesized, structurally characterized much later, but then it turned out to be a complete square. Now, what is so significant about it is the fact that if it is a square triplet, and if it's a square, then you would have expected this molecule to have two unpaired electrons. But it was predicted that it will form a square cyclobutadiene coordinated to FeCO3. Not only that, it will be a diamagnetic system. And indeed, it was a diamagnetic system. So this was one of the early great victories for molecular orbital theory, because they were able to use MO theory to predict the formation of this molecule and the electronic structure of this molecule. So here is the structure of the molecule. I'm sorry. These are calculated values. This is the triplet 1.44. What you notice is that the moment it is coordinated to FeCO3, the bond distance between the two carbons has become 1.43. Okay, and that is longer than 1.33. So the bond distance has in fact elongated from 1.33 to 1.43. So that is consistent with the Duer-Chat-Duncanson model. And this distance is for the triplet. Okay, so these distances are for the triplet. So it is moving towards the geometry of the triplet. So why is this happening? You can figure it out from Duer-Chat-Duncanson model, that you have removed electron density from psi2 and pushed it into psi3. A same situation, but now the species are slightly changed. What is happening is that these two hydrogens, which were the offending hydrogens bumping into each other and causing steric congestion, has been removed, and a carbon-carbon bond has been formed. This is in fact a classic way by which steric interactions can be removed. You remove the offending atoms and form a covalent bond, and that's what is being done in this case. And you have a system where you have cyclobutadiene coordinated to I'm sorry, I should have opened this structure, but I will show it to you in 3D in a second. So here you go. This is a perfect square. Okay, and you have iron tricarbonyl coordinated to a perfect square, and notice how flat this whole molecule is. So it's really an amazing victory for theory, in that it was able to predict this molecule before it was even synthesized. This is of course iron. So this is iron molecule, okay, iron atom. So let me proceed now with the structure. So what else is significant about this? You can make the nickel 2 complex also in this particular case, and this was done by treating it with dichlorocyclobutene. One nickel is oxidized to nickel. and the nickel dichloride is coordinated to the cyclobutadiene. And here is iron, the complex that I showed you. That is also made. This is plus FeCl2. So this also results in the formation of FeCl2. So what is interesting is that because it is a square molecule now, there is perfect conjugation between the 4 carbon atoms, and this is looking like an aromatic. Surprisingly, what they found was that chemistry was also like that. You could treat it with AlCl3 and acetyl chloride and generate acetyl cyclobutadiene coordinated to FeCO3. So this is very typical of an aromatic solution. So now cyclobutadiene was anti-aromatic. Okay, it was rectangular, square, and it has been made. It was anti-aromatic, and this has now been made aromatic. So the iron completely changes the electronic structure of this molecule. So the of this molecule is also indicative of such changes. All 4 carbon atoms have a resonance of 65 ppm, 65 ppm, which is similar to what you have in the average of the 2 carbons which are present in simple butadiene coordinated to FeCO3. This is, like I told you, the metal complexes have weird chemical shifts, but in general they shift it. In this particular case, the terminal carbon is different from the internal carbons, and when you make cyclobutadiene becomes equivalent and everything is the same. So compared to carbon-13 NMR of free ethylene, the ethylene complex, the chemical shift is upfield. So this is what I told you about the effect of the large amount of electron density that is present on the metal. We can proceed to the next system, which is, can we make a metal triene complex? Is it possible for me to make a metal triene complex? And the answer is yes and no. The no comes because the steric interaction between the hydrogens of I'll just get my the yeah. So I think I have it drawn out, so I don't have to draw it again. Let me just show you there are 2 hydrogens which are on the terminal carbons, and they are going to bump into each other very. So this type of an interaction between the 2 hydrogens, they're going to be bumping into each other. So these type of complexes are not stable. It is better to remove them and to form a covalent bond. So you just remove this, you remove these 2 hydrogens and form a bond here. And that gives you a benzene complex. And in fact, that's what is very easy. Okay. There is, of course, another way of doing it, and that is to put 2 groups which can interact, and that is formed. That is heptatriene. Heptatriene complexes are also known. Heptatriene is also known, and they do form stable complexes. This is clear from this example because this is possible and this is not stable. It's very clear that it is a steric phenomenon. Three double bonds in sequence conjugated to each other can form nice metal atoms. This is the distance arrangement in the triene complex, and what you find is it's not an aromatic system. It is actually a bond alternating system. Isolated single bonds and double bonds are formed. You can see that the bond, and that is fixed, and so you do not have a benzene which is coordinated. It is actually a triene which is coordinated to the molybdenum. Okay, now of higher valent metal chlorides or metal salts with a good reducing agent. In the example that is shown for you in the literature, in the screen, it is in fact sodium amalgam reducing zirconium to zirconium 0, and it's forming a 16 valence electron complex. So this is still electronically unsaturated. Now let me proceed to another complex, and that is a complex which is got 4 double bonds. In this case, it is not possible to form a stable complex with a single metal atom because the span, the distance is very large. So unless you have a very large metal atom which can interact with both 1 and 5, 1, 2, 3, 4, 5, yeah, between both 1 and 5 and 1 and 6, then only you can have such flat rings. I think the actinides and lanthanides are probably big enough for such interactions. I do not have an example right here to show you, but 3D, 4D, and 5D elements do not form such complexes. Instead, they form complexes which are tub-shaped. 4 double bonds in cyclooctatetraene, for example, form a complex with 2 metal atoms. And the 2 metal atoms on either side of the tub, I'm talking about this as the tub. This is the tub. And on both sides of the tub, there are 2 metal atoms. In fact, the top metal atom is interacting with the top carbon atoms. So let's label them. 1, 2, 5, and 6 are interacting with M1. M2 is interacting with 3, 4. Maybe we can color code them here. Then you can. It's easy for you to, when you review it. Okay, so the blue is interacting with the blue carbons and the green is interacting with the green carbons. And these molecules are, they don't sit quietly, they keep moving around. And as a result, many of them are fluxional. The tub can be the way in which I showed you. They can also be like a step. So that is the tub structure. This is the step structure. So all these structures are available, and I think I have some link. but these links are not opening, so I'm going to see if it works, but if it doesn't work, I will go, I'll keep going. If the link opens, I will show the structure for you. Oh, yeah, yes, I can show you the structures. Okay, so here is the cyclooctatetraene structure, in which there are two atoms, one on the top and one on the bottom. This is platinum on the top and platinum on the bottom interacting with cyclobutadiene. And here is the uranium structure. I will show you the uranium structure also. Uranium has got, it's big enough for all 8 carbons to interact with the uranium. So this is the uranium. Okay, that is not very clear what element it is. I'll have to find out, is it thorium or I'll have to find out what it is. Okay, but these are structures where it says uranium on my in my screen, but here it shows titanium. So I'm a bit confused. I'll find out and clarify. Okay. These are 2 examples which I have shown for you just for synthesis. An abstraction reaction. These principles are general. I have already shown for want to make a cationic complex here. In this particular case, it forms a nice 7-membered ring with vanadium. By the way, early transition metals do have a tendency to interact with these large rings, and that is because they are electron deficient, and the molecule is not as surprisingly, these molecules are so I don't have the cycloheptatrienyl. It is actually not pseudo, and interacting with 2 vanadium.
Sir, your video is getting frozen sometimes.
It says bad network quality, and I checked the network quality in the morning. It seems to be good, but I'm not able to help it. I have checked this problem. Today, the network seems to be erratic a little bit between Microsoft Teams, and the problem is between Teams and the institute. It's not really a problem between my computer and the network center. Okay. So, are you able to see the metal atom ligand co-condensation?
Sir.
Okay. So this is, of course, a unique way of making the metal complex, and where you just vaporize the molybdenum. You vaporize the molybdenum by heating it, resistive heating. The minus 196 degrees is on the ligand side. It is frozen on the surface of a vessel. Usually what happens is you take a large vessel and you put it in liquid nitrogen. That's where the minus 196 comes from. And you do resistive heating. You put your metal here and vaporize it. And the metal evaporates and condenses on the sides along with the C7H8. Which is condensed on the surface. Okay, I have to show it to you in a different color. This is C7H8 is condensed on the surface of this vessel, and the molybdenum atoms are also condensing on the molybdenum is also condensing as atoms. Because the molybdenum now has got no other species to interact with, it's a single atom. It interacts with a ligand very efficiently and forms a complex. You can also start with molybdenum hexacarbonyl and knock off 3 carbon monoxides. In this particular case, the knocking off is through heat. And in this case, the tungsten complex, it is formed, this FACT complex has been formed first. 3 acetonitrile ligands are there. R equals Me is acetonitrile. 3 acetonitrile ligands and 3 carbon monoxide ligands are there. Acetonitrile is a poor ligand, so minus 3 CH3CN gives you, and plus C7H8 gives you this complex. Okay. Between a conjugated and a non-conjugated double bond. Some metals prefer conjugated double bonds. Some metals prefer non-conjugated double bonds. So if you take cyclooctadiene, 1,3-cyclooctadiene, this is 1,3-cyclooctadiene, and treat it with some metal atoms, it will form a nice complex. On the other hand, if I treat it with a metal which prefers 1,5 structure, okay? Since we have not studied isomerization, I'm not going to talk about 1,3-cyclooctadiene and treat it with Fe2CO9, it forms a nice compound with FeCO3. Okay. On the other hand, if I take Fe2CO9 and treat it with 1, now conjugated, it has isomerized the 1,5 to 1,3-cyclooctadiene. So this type of isomerization is promoted by the preference of the ion for a conjugated double bond. So this is an electronic preference of the ion atom for conjugated double bond. There are other species which prefer rhodium-1, for example, prefers the non-conjugated system. So both possibilities are there, and these are shown here. For example, this is what you expect, and what you end up with is the 1,5 system. Okay, so it prefers the isolated double bonds. So I want to stop here because I think it's time. I will stop here. But this is both atoms are both rhodium and iron are able to isomerize the double bonds to the system of their choice. This is both in terms of size and in terms of electron donation. You can think about it and let me know why. This is, take it as an assignment. Why is it that rhodium prefers the non-conjugated system and iron prefers the conjugated system? Any questions? I think the network is poor today, but if there are any questions,
Sir, can you go to the slide where you showed the change in the length of the bonds of cyclobutadiene on coordination with FeCO3?
yeah.
Yeah, sir, here the opposite bond should have been the same length, 1.431.
1.419, I think, is for this distance.
Oh,
And
okay.
yeah,
Right.
I
Yeah,
think
they
this,
all same length.
yeah, they are all the same.
Yeah.
We could have looked at it in the three-dimensional structure also. It's a perfect square.
Yeah.
So I can just show you here in a minute. I think it is 1.43 and 1.43 exact. You can see that distance. It's exactly 1.43, 1.43. It's in fact symmetry related. So yeah, I think there is a mistake in the bond distance marking that I have made. 1.4 is very small. This is 2.03. So I think there is a mistake in that slide. I should correct it. Any other question? Okay, if there are no questions, then we end today's class. There. So that will be the class. And next Monday will be the test.
Sir,
Yes.
sir, next Monday is 30th, but you said that 2nd December will be the test.
Which day? Wednesday. Huh? It's
Okay,
Wednesday,
sir.
right? Yeah. Yeah, whatever date I have posted, that will be the date on which the test is then. Yes.
Hello, sir.
Yeah.
Sir, in the top shape, where you showed the cyclooctatetraene with which is conjugated with two metal. Hello, sir.
Yes, I can hear you.
Sir, is two platinum carbon distance, or it is a single one, as the top shape is not is functional. I'm not putting it in the right words actually. Hello, sir.
Yes, this one.
Yes, sir. Sir, here the cyclooctatetraene is fluxional, right?
Okay. Let me tell you something. This is in the X-ray structure.
It is
What
like
you see is a static form.
static form, yes.
Yeah. But what I told you as fluxional is that in many cyclooctatetraene molecules, the metal is able to move from one position to the other position.
Okay, sir.
Okay. So for example, these molecules are capable of moving from one position to the other. In NMR studies, they have shown that they are capable of moving, but I did not refer to specifically the platinum case, but in general, it is capable of moving.
Sir, here one thing is happened that the top can flip and the two metal atom can form two a single bond. So in some measurements we can get only one type of PTC bond. Is there any proof of that, or is here two PTC bonds observed in everywhere? Can you understand my point?
I'm a bit confused. This is one distance, and this is another distance, and these are slightly different, 2.26 and 2.27.
Okay.
Okay, so what was the question that you asked?
Sir, here the cyclooctatetraene can flip, right? If metal can, if metal is fluxional, then cyclooctatetraene can flip. So, some measurements where some slow measurements where you cannot detect the flipping, there we can observe only two types of bonding that you show that here. Hello, sir.
Okay, yeah, I heard what you said, but I think what you are referring to is that if the measurement technique is slow, then it will measure an average distance.
Yes, sir.
But what I mentioned in earlier to the previous question was that in the crystal structure, you observe a static form, and
Yes,
generally it is not moving at the temperatures that at which you're doing a crystal structure. It is static.
okay, sir.
Yeah. Not much scope for movement in crystal structures usually.
Yes, yes, sir.
Okay. Okay.
Hello, sir.
Yes.
Sir, in the pre-synthesis of carbene, sodium hydride is added generally. So, why potassium tertiary butoxide catalytic amount of each catalytic amount is added? What is
Where?
the role of?
Where?
Sir, in the pre-synthesis of any carbene, like IMS or IDIP carbene.
There it is not catalytic amount, it is the stoichiometric amount of base is added to remove.
Yes, sir. Sodium hydride is taken as a stoichiometric amount, but along with that, a catalytic amount of tertiary potassium tertiary butoxide is also added.
Got it. Okay. Good. So this is sometimes it's a phenomenon that has been quite a bit popularized by a Japanese scientist. I think Shibashaki or somebody. This is multiple bases are used, and it has been shown that they are better than single bases. I don't understand the theory.
Hello, sir. Hello. Hello, sir.
You're not able to hear?
Yes, sir. Your voice was lost.
Okay. So if I use two bases, it has been empirically shown to be better than a single base. I don't have a good theoretical explanation for this.
Yes, sir. Yes.
Maybe there is, but this is a well-known phenomenon. When I have a second, mixed base, then the mixed base is better than a single base.
Yes, sir. Yes, sir. Thank you.
Okay. I think it's Shibashai. It was a Japanese scientist. It does a lot of this work. Yeah. If there are no other questions, I'm going to stop the video now and we'll continue on Wednesday.